Hello, friend. In this video, we'll wander together through the wonders of the universe, from the birth of stars and galaxies to the forces that shape them and the quiet whispers of the cosmic microwave background. Along the way, we'll uncover the dance of light and gravity, explore the mysteries of dark matter and dark energy, and gently ponder our place in this vast cosmic story. Let's begin this calming journey through the cosmos and see where the quiet light of the universe leads us. Chapter 1. What is astrophysics? Astrophysics is the branch of science that seeks to understand the fundamental workings of the universe by applying the principles of physics to celestial objects and cosmic phenomena. Unlike observational astronomy, which catalogs and maps what we see in the sky, astrophysics asks deeper questions. It wants to know what stars are made of, why galaxies form the way they do, and how black holes warp the very fabric of space and time. Through this exploration, astrophysics bridges the gap between what we observe and why it exists. At its heart, astrophysics unites the vast expanse of the cosmos with the smallest, most fundamental forces and particles that govern nature. It's an interdisciplinary field, combining insights from classical mechanics, electromagnetism, quantum physics, and relativity to explain everything from the faintest glimmer of a distant star to the immense energies released in supernova explosions. The term astrophysics itself emerged in the mid-19th century as astronomers began to use the tools of spectroscopy to analyze starlight. Before that, astronomy had been largely descriptive, concerned with recording the positions and motions of stars and planets. But when scientists discovered that the spectrum of light from the sun and stars revealed their composition, temperature, and motion, astronomy expanded into a more profound scientific endeavor. This shift marked the birth of astrophysics, the marriage of astronomy and physics into a single, powerful lens through which we explore the universe. One of the central principles in astrophysics is the universality of physical laws. This idea states that the laws we test and confirm on Earth also apply in the most distant reaches of space. When we see the same spectral lines of hydrogen in a distant quasar that we see in a laboratory on Earth, we're observing the same atoms obeying the same rules, despite being separated by billions of light years. This principle allows astrophysicists to make predictions and test theories about phenomena that are far beyond human reach. For instance, we cannot visit the core of a massive star, yet we can use the equations of nuclear fusion, verified in laboratories and particle accelerators, to model how stars burn hydrogen into helium and heavier elements. Similarly, we rely on the well-tested laws of gravity and general relativity to explain the motion of galaxies and the bending of light around massive objects. Another cornerstone of astrophysics is that the information we receive from the cosmos arrives as light in its broadest sense. From radio waves to gamma rays, the entire electromagnetic spectrum carries clues about the universe's history and composition. Optical light, which we see with our eyes, is just a small fraction of this spectrum. Astrophysicists use specialized instruments, telescopes that operate at different wavelengths, to collect and analyze this light. Radio telescopes map cold gas clouds that birth new stars. Infrared telescopes peer through dusty nebulae to glimpse star-forming regions. Ultraviolet and X-ray telescopes reveal the high-energy environments near black holes and neutron stars. Gamma-ray observatories catch brief, violet bursts from the deaths of massive stars or the merging of exotic stellar remnants. By combining these observations, astrophysicists piece together a multi-wavelength portrait of the cosmos. Each portion of the spectrum offers a different perspective, much like viewing a single scene under various lights. This comprehensive view allows scientists to understand the life cycles of stars, the dynamics of galaxies, and even the large-scale structure of the universe. To interpret these observations, astrophysics draws upon several key areas of physics that together form the theoretical backbone of the field. Classical mechanics describes the motion of objects, from orbiting planets to interacting galaxies. Newton's laws of motion and his law of universal gravitation provide the framework for understanding how objects attract and move in response to gravitational forces. Thermodynamics governs the transfer of energy in stars, explaining how heat and radiation flow within celestial bodies. The balance of energy transport determines a star's size, temperature, and lifespan. Electromagnetism, captured in Maxwell's equations, describes how electric and magnetic fields interact, essential for understanding how light propagates through space and how magnetic fields shape cosmic structures. Quantum mechanics explains the behavior of atoms and particles at the smallest scales, crucial for understanding atomic spectra, nuclear reactions in stars, and the behavior of matter under extreme densities. General relativity, developed by Albert Einstein, describes how mass and energy warp the fabric of space-time itself. This becomes essential when studying massive objects like black holes and the expansion of the universe on cosmological scales. These pillars of physics allow astrophysicists to move beyond mere observation, enabling them to build theoretical models that can be tested against the data collected by telescopes and observatories. One of the remarkable features of astrophysics is its ability to connect the smallest and largest scales of nature. The nuclear reactions that power a star occur within atomic nuclei, while the same star's gravitational influence can shape the orbits of planets light years away. On a grand scale, astrophysics explains how clusters of galaxies, spanning millions of light years, form from tiny fluctuations in the density of matter just after the Big Bang. These fluctuations, imprinted in the cosmic microwave background, grew over billions of years under the pull of gravity to become the vast cosmic web of galaxies we see today. Astrophysical processes also reveal the interplay of the four fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. In the cores of stars, the strong force binds protons and neutrons, allowing nuclear fusion to release tremendous energy. Gravity contains this energy, shaping the star's structure. The light emitted by fusion is carried outward by radiation and eventually escapes to space, where it travels for eons to reach our telescopes. A central method in astrophysics is the cycle of observation, theory, and prediction. Observations provide data, images, spectra, timing measurements that capture the state of celestial objects. Theories attempt to explain these observations using the laws of physics to build models that can account for what is seen. For example, the discovery of pulsars, rapidly rotating neutron stars that emit beams of radiation, challenged astrophysicists to develop theories of how magnetic fields and relativistic effects work in such extreme environments. The interplay of observation and theory sharpened our understanding of these dense, exotic objects. Similarly, observations of the motions of galaxies revealed that they rotate faster than visible matter alone would allow. This discrepancy led to the hypothesis of dark matter, an unseen substance that exerts gravitational influence, yet does not emit or absorb light. Decades of observations and theoretical work have confirmed dark matter's role as a dominant component of cosmic structure. Astrophysics remains a vibrant, evolving field. Questions that once seemed unanswerable, like the nature of black holes or the origins of elements, are now explored with precision instruments and powerful supercomputers. Yet new questions constantly emerge. What is the true nature of dark energy, the mysterious force causing the universe's expansion to accelerate? What happens to matter at the heart of a black hole, where gravity overwhelms all other forces? Are there other forms of life in the universe, hidden in the atmospheres of exoplanets or the icy oceans of moons? These mysteries drive the work of astrophysicists, inspiring the design of new observatories and the refinement of theories that seek to unify the known forces of nature. Beyond its scientific scope, astrophysics offers a profound perspective on humanity's place in the cosmos. It reminds us that the atoms in our bodies were forged in the hearts of ancient stars, stellar crucibles that lived and died long before Earth itself took shape. It shows us that we are part of a universe that is dynamic and evolving, governed by laws that link the flickering of a distant quasar to the glow of a candle's flame. This perspective can be both humbling and uplifting, revealing our connection to a vast, interconnected whole. As we gaze into the depths of space, measuring the light from galaxies billions of years old, we are not merely gathering data. We are witnessing a tapestry of existence woven over unimaginable spans of time. In every observation, we find echoes of the same forces that shape our own lives. Gravity that binds us to Earth, light that warms our days, and the elements in our blood and bones that once shone in ancient stars. Astrophysics, then, is more than a scientific discipline. It is a gentle reminder that, in the vastness of the cosmos, we find both our origins and our destiny, forever intertwined in a universe that continues to reveal its secrets to those who seek with patience and wonder. Chapter 2: Tools of the Cosmos, Telescopes and Detectors. Astrophysics, like all scientific fields, relies on tools that allow us to observe, measure, and understand the universe. Chief among these are telescopes and detectors, instruments that transform the faintest glimmers of distant stars into data that can be analyzed and interpreted. These devices are the eyes of astrophysics, opening windows to the vastness of space that would otherwise remain forever beyond our reach. A telescope, at its most basic, is a device that collects light. Unlike the human eye, which has a limited aperture and can only gather so much light, telescopes have much larger apertures that collect far more light, revealing fainter and more distant objects. By capturing more light, a telescope can also reveal finer details, turning tiny points of light into complex structures, spiral galaxies, star clusters, nebulae. This ability to gather and focus light makes telescopes essential for studying the cosmos in all its rich complexity. The principle of focusing light can be achieved through two main designs: lenses and mirrors. Refracting telescopes use lenses to bend and concentrate light, much like a magnifying glass focuses sunlight to a point. Reflecting telescopes, on the other hand, use curved mirrors to gather and redirect light to a focal point. Both designs have their advantages and limitations, but mirrors tend to be favored for large telescopes because they can be made much larger and lighter than lenses. The most powerful ground-based telescopes today rely on mirrors that span many meters in diameter, carefully polished and precisely aligned to collect light from the farthest reaches of the universe. Detectors are the other half of the equation. While telescopes collect and focus light, detectors measure and record it. In the early days of astronomy, this role was filled by the human eye, or photographic plates that captured the light as chemical reactions on glass. Today, electronic detectors, such as charge-coupled devices, CCDs, are used to convert light into digital signals that can be analyzed with computers. These detectors are incredibly sensitive, able to detect single photons of light, and they provide a level of precision and consistency that was once unimaginable. Beyond visible light, telescopes and detectors are designed to capture the entire electromagnetic spectrum. Each region of the spectrum, radio, infrared, ultraviolet, X-ray, gamma ray, requires different materials and designs to collect and measure its unique properties. Radio telescopes, for example, use large parabolic dishes to gather long wavelength radio waves, while X-ray telescopes rely on special mirrors that can reflect high-energy photons at shallow angles. Each of these instruments reveals a different aspect of the cosmos, offering insights that would be hidden if we relied solely on the light our eyes can see. Ground-based observatories are often built in remote, high-altitude locations to minimize the blurring effects of Earth's atmosphere. The thin, dry air reduces the distortion of starlight and allows for clearer, sharper images. In some cases, astronomers use adaptive optics, systems that adjust the telescope's optics in real time to correct for atmospheric turbulence. These corrections help ground-based telescopes approach the clarity of images taken from space. Space-based telescopes avoid the atmosphere altogether by orbiting above it. Instruments like the Hubble Space Telescope and the James Webb Space Telescope have provided views of the cosmos with unprecedented clarity, free from the shimmering distortion of Earth's air. Space telescopes can also access wavelengths of light that are absorbed by the atmosphere and never reach the ground, such as ultraviolet and X-rays. These observations open up entirely new windows on the universe, revealing phenomena that would otherwise remain hidden from view. Calibration is a crucial part of using telescopes and detectors. Even the best instruments can introduce subtle distortions or biases in the data they collect. Astrophysicists use carefully measured light sources and known standards to calibrate their instruments, ensuring that the data reflect the true properties of the light from celestial objects. This meticulous work allows for meaningful comparisons between observations and theoretical predictions, helping to refine our models of the universe. The data gathered by telescopes and detectors are often stored in massive archives, forming a collective memory of the universe as seen from Earth. These archives contain decades of observations, from the first images of distant galaxies to the faint signals of cosmic microwave background radiation. Astrophysicists sift through these vast repositories to uncover patterns, track changes, and test new theories. The accumulated data provide a foundation for understanding how the universe evolves over time. Modern telescopes and detectors are also designed to work together in networks and arrays. Radio telescopes are often linked in interferometric arrays that combine signals from widely separated antennas, creating images with the resolution of a telescope as large as the distance between them. Optical and infrared telescopes participate in time-domain surveys, scanning large areas of the sky repeatedly to detect transient events like supernova and variable stars. These collaborative efforts allow astrophysicists to observe the dynamic nature of the cosmos and to catch brief, energetic phenomena that might otherwise be missed. The interplay of telescopes and detectors is not limited to passive observation. Some instruments are designed to actively probe the universe, sending out signals and measuring their reflections or responses. Radar astronomy, for instance, uses radio waves to map the surfaces of planets and asteroids. Laser ranging can measure the distance to the moon with astonishing precision. These active techniques complement the passive collection of light, providing a fuller picture of celestial objects and their behaviors. As technology advances, so too do the capabilities of telescopes and detectors. New materials, improved electronics, and sophisticated data analysis techniques continually push the boundaries of what can be observed and measured. Future telescopes will be able to image exoplanets directly, detect the faint glow of the first galaxies, and perhaps even capture the echoes of gravitational waves from the birth of the universe. This ongoing journey of building better telescopes and more sensitive detectors is driven not only by a scientific desire to test theories and gather data, but also by an enduring curiosity about what lies beyond our familiar world. New instruments are designed with careful consideration of how light interacts with matter, how detectors can be cooled to reduce noise, and how complex data can be analyzed to reveal hidden structures in the sky. In modern astrophysics, the interplay between telescope design and detector technology is a marvel of precision and innovation. Scientists meticulously choose coatings for mirrors and lenses that maximize light collection while minimizing distortion. They develop detectors that can distinguish between the faint glow of a distant galaxy and the background noise of the cosmos. Every advancement brings us closer to seeing deeper into the universe and to answering questions that once seemed beyond our reach. Perhaps one of the most profound aspects of this work is the sheer scale of it all. Telescopes and detectors, in their quiet watchfulness, are constantly gathering light that has traveled across billions of years. That light, bent and scattered by dust and gas, carries the faintest whispers of the universe's past. By capturing it, we are not just looking outward, we are looking back in time, tracing the evolution of galaxies, stars, and cosmic structures from their birth to the present. In the end, telescopes and detectors are more than just tools. They are extensions of our senses, amplifying our ability to perceive and understand the vastness around us. They allow us to see beyond the limits of our own eyes, to measure forces and energies that we can barely comprehend. Through them, we transform ancient starlight into knowledge, and fleeting glimpses of the sky into a coherent narrative of the cosmos. The observatories themselves, whether nestled in remote mountain ranges or floating in the void of space, stand as monuments to human ambition and creativity. These facilities, equipped with their meticulously crafted mirrors and detectors, work tirelessly to capture fleeting photons that have traveled unimaginable distances. Each photon, no matter how faint, carries information that adds another brushstroke to our ever-expanding portrait of the cosmos. The data collected by telescopes and detectors do not remain isolated. They are shared across networks of scientists, integrated into broader studies, and compared with theoretical models that stretch the boundaries of human understanding. This collaboration, spanning continents and cultures, represents a shared journey to unravel the universe's secrets. In this shared quest, instruments become more than machines. They are silent witnesses to the interplay of light and matter, echoes of the fundamental forces that bind the universe together. As each new telescope begins its vigil, and as each new detector records its first photons, there's a sense of anticipation that pulses through the scientific community. What hidden galaxies will emerge from the darkness? What transient phenomena will be caught in the moment of their fleeting brilliance? These questions propel astrophysicists to push the limits of technology, to refine the delicate balance of optics and electronics that bring distant worlds into focus. In these quiet, patient pursuits, there's a subtle poetry. The cold precision of the detectors, the smooth sweep of the telescope across the sky, the hush of a control room as the first images appear. These are the moments when science and wonder converge. It is in this union that the work of astrophysics becomes more than data and equations. It becomes a meditation on our place in the universe, a reminder that even as we measure and record, we are also participants in the unfolding story of existence. For in the glow of distant galaxies, in the quiet hum of an instrument waiting for starlight, there lies a gentle reminder that the universe is not just a collection of objects to be cataloged and analyzed, but a vast and intricate dance of forces and energies playing out across time and space. And in the soft glow of each observation, there is a call to look deeper, to wonder at the infinite, and to find within it the faint but unwavering echo of our own curiosity. Chapter 3. The Nature of Light, Spectra, and What They Reveal. Light is the messenger of the cosmos, carrying with it the stories of distant worlds and ancient events. In astrophysics, light is more than just a source of illumination. It is the primary tool for understanding the universe. Each photon that reaches our detectors has traveled vast distances, and along its journey it has been shaped by the environments it passed through. The study of this light, Its colors, its intensity, and the way it shifts is at the heart of astrophysics. This process is known as spectroscopy. When we examine the light from a star or galaxy, we are not merely seeing a glow in the sky. We are witnessing a complex interplay of physics. Light is an electromagnetic wave, oscillating electric and magnetic fields that travel through the vacuum of space. As it moves, it interacts with matter, revealing the properties of whatever it encounters. By studying these interactions, we can uncover the composition, temperature, motion, and structure of objects that are otherwise inaccessible. Spectroscopy begins with the realization that light can be spread out into a spectrum, much like sunlight passing through a prism to form a rainbow. Each color in this spectrum corresponds to a different wavelength, and each wavelength carries information about the source of the light. A spectrum is more than just a beautiful array of colors. It is a scientific fingerprint that encodes the secrets of the universe. In astrophysics, spectra reveal three fundamental types: continuous, emission, and absorption. A continuous spectrum shows a smooth, unbroken range of colors produced by hot, dense objects like stars or incandescent solids. Emission spectra, on the other hand, consist of bright lines at specific wavelengths, emitted by atoms and molecules as they release energy. Absorption spectra show dark lines superimposed on a continuous background, created when cooler gas absorbs specific wavelengths of light from a hotter source behind it. The dark lines in an absorption spectrum, for example, are signatures of the elements present in a star's atmosphere. Hydrogen, helium, sodium, and many other elements each absorb light at characteristic wavelengths, leaving behind distinct fingerprints that can be used to identify them. By measuring these lines, astrophysicists can determine the chemical composition of stars and galaxies, even when they are light years away. This knowledge is essential for understanding the life cycles of stars, the formation of planets, and the enrichment of the cosmos with the elements necessary for life. Beyond composition, spectra also reveal the temperatures of celestial objects. The color of a star's light depends on its surface temperature, with hotter stars appearing bluer and cooler stars redder. By analyzing the shape and intensity of a spectrum, astrophysicists can calculate the temperature of a star's outer layers with remarkable precision. This information helps us map the stages of stellar evolution and understand the balance of energy within these distant suns. Spectroscopy also allows us to measure motion in the universe through the Doppler effect. When an object moves toward us, the light it emits is compressed to shorter wavelengths, shifting toward the blue end of the spectrum. Conversely, when an object moves away, the light is stretched to longer wavelengths, shifting toward the red. By measuring these shifts, astrophysicists can determine the speeds at which stars and galaxies are moving, unveiling the dynamic nature of the cosmos. The use of spectroscopy extends beyond individual stars and galaxies. It allows us to probe the vast spaces in between, where clouds of gas and dust drift through the void. The light passing through these clouds carries the imprints of their presence, revealing their density, temperature, and even their chemical makeup. In this way, spectroscopy acts as a cosmic probe, mapping the unseen structures that shape the evolution of galaxies and the flow of matter in the universe. Each spectrum is a story, written in light and waiting to be read. The patterns we see are not static. They change over time as stars evolve, as galaxies collide, and as the universe itself expands. By collecting and comparing spectra from different times and places, astrophysicists can reconstruct the history of the cosmos, piece by piece. This ongoing work requires meticulous observation, careful calibration, and the continual refinement of theories to match what we see. In modern astrophysics, spectroscopy is a field of both subtlety and power. The instruments that capture these spectra must be finely tuned, capable of detecting the faintest traces of light from across the universe. They must be cooled to near absolute zero to reduce noise and sharpen the signal. And they must be calibrated against known standards to ensure accuracy. This meticulous work is a testament to the precision of modern science and the dedication of those who seek to understand the cosmos. Yet, for all its precision, there is something almost poetic in the way spectra reveal the universe. Each line, each curve in the spectrum, is a direct connection to a distant object, a bridge across the gulf of space and time. It is a reminder that the universe is not silent. It speaks to us in the language of light, a language that we are only just beginning to fully understand. Spectroscopy has also allowed scientists to identify molecules in distant environments, opening a window to the chemistry of the cosmos. In the atmospheres of cool stars and giant planets, molecules leave distinct spectral features that reveal the presence of water vapor, carbon dioxide, methane, and other compounds. By analyzing these subtle molecular signatures, astrophysicists can infer the physical and chemical conditions in alien worlds, drawing connections between the familiar processes on Earth and those at work in the distant reaches of the galaxy. As we look beyond our solar system, spectroscopy becomes an essential tool for the study of exoplanets. When a planet passes in front of its star, some of the starlight filters through its atmosphere, imprinting a faint signature in the spectrum that tells us about the planet's gases. In this way, we can detect traces of elements and molecules that hint at possible climates and perhaps even the conditions for life. These observations demand extreme precision, for the signals are often faint and buried in the glow of the parent star. Yet with careful measurement and patient analysis, these tiny imprints reveal entire worlds otherwise lost to the darkness of space. Spectroscopy also plays a crucial role in measuring the expansion of the universe itself. As galaxies recede from us, their light is stretched by the expansion of space, shifting spectral lines to longer, redder wavelengths. This cosmological redshift encodes information about the rate of expansion and the age of the universe, allowing us to trace the evolution of cosmic structures over billions of years. By studying these shifts in the spectra of distant galaxies and quasars, astrophysicists map the large-scale structure of the cosmos and test our deepest theories about its origin and fate. The craft of spectroscopy is as much an art as it is a science. Each spectrum is carefully extracted from observations that may take hours or even days to collect, requiring instruments to be precisely aligned and detectors cooled to minimize noise. Once captured, the spectrum must be calibrated and corrected for the distortions introduced by instruments and the atmosphere. This painstaking work requires not only technical skill, but a deep understanding of the subtle ways in which light can be altered and obscured on its journey to our instruments. In laboratories and observatories around the world, scientists work in quiet rooms, bathed in the glow of computer screens, displaying the delicate traces of spectra. They adjust the data, compare it to models, and search for faint features that might reveal a new star, a distant quasar, or the thin atmosphere of an exoplanet. Each spectrum is a dialogue with the universe, a conversation carried out in the language of light. As technology advances, the detail and precision of spectra continue to improve. Instruments aboard spacecraft and observatories in orbit gather light that has never touched Earth's atmosphere, preserving its purity and extending our reach into the cosmos. Ground-based telescopes, equipped with adaptive optics and ever more sophisticated spectrographs, reveal features in the spectra that were once hidden by the blurring of our air. In this union of precision and passion, scientists and engineers push the limits of what can be seen and measured. In these faint lines and subtle curves, there's a story of creation and destruction, of calm and violence, of birth and death on a cosmic scale. The spectra of supernovae show the final moments of massive stars, their light echoing across the galaxy as they seed the cosmos with heavy elements. The spectra of active galactic nuclei reveal the voracious appetites of supermassive black holes, devouring matter and releasing torrents of energy. Even the soft glow of the interstellar medium, captured in the faint emission lines of ionized gas, tells of the slow dance of matter as it cycles through generations of stars. To the patient eye, spectra offer more than just data. They offer a glimpse into the timeless processes that shape the universe, processes that unfold over millions or even billions of years. In the quiet light of these distant sources, there is an echo of the vast scales of time and space that define our cosmos. Each photon, each spectral line, is a message from a time and place far removed from our own, yet bound by the same laws that govern the world around us. In the end, the study of light and spectra in astrophysics is a testament to human curiosity and ingenuity. We have taken the simplest of tools, a prism splitting sunlight, and turned it into a means to read the deepest secrets of the universe. Through patient observation and careful analysis, we have learned to see beyond what is visible, to hear the whispers of ancient stars, and to trace the paths of galaxies across the ages. And in those final moments of contemplation, when the lines of a spectrum fade into the silence of the night, there is a soft, persistent echo, a reminder that in seeking to understand the light of distant worlds, we also illuminate the wonder within ourselves. It is a gentle hum that bridges the cold precision of science with the warmth of human curiosity, whispering that even in the darkness of space, there is always light to guide us. Chapter 4. The Life Cycles of Stars from Birth to Remnants. The life cycle of a star is one of the most fundamental narratives in astrophysics, weaving together the interplay of gravity, pressure, nuclear fusion, and the cosmic alchemy that creates the elements of the universe. Stars are born from vast clouds of gas and dust known as molecular clouds that exist throughout galaxies. These clouds, cold and dense, provide the raw materials for stellar formation. Within them, tiny fluctuations in density can trigger a collapse, drawing more and more material inward. As a region within a molecular cloud collapses, it forms a dense core that grows hotter and denser at its center. The gravitational contraction converts potential energy into heat, and as the temperature rises, the cloud begins to glow faintly in the infrared, marking the birth of a protostar. The protostar stage is a time of gathering and growth, as material from the surrounding cloud continues to fall inward, feeding the growing mass of the young star. The formation of a star reaches a turning point when the core temperature becomes high enough for nuclear fusion to ignite. Hydrogen atoms begin to fuse into helium, releasing energy that counteracts the pull of gravity. The star achieves a delicate balance between the inward force of gravity and the outward pressure from fusion, settling into the main sequence phase of its life. This equilibrium can endure for billions of years, depending on the star's mass, as it steadily converts hydrogen into helium and shines with a steady light. During its time on the main sequence, a star's properties are determined largely by its mass. More massive stars burn hotter and brighter, consuming their hydrogen fuel at a much faster rate. They live short, intense lives compared to smaller stars, which can shine in steady light for billions of years. The Sun, a medium-sized star, will remain in this phase for roughly 10 billion years, maintaining the balance that makes life on Earth possible. But even the main sequence is not a permanent state. As hydrogen in the core is depleted, the balance begins to shift. The core contracts under gravity, heating up as it does, while the outer layers of the star expand and cool. This expansion marks the transition to the red giant phase for stars like the Sun, or the more luminous supergiant phase for more massive stars. The star's outer envelope swells outward, its light turning redder and its shape more diffuse. Within the core, the increasing temperature and pressure allow helium to fuse into heavier elements like carbon and oxygen. This stage of helium burning is shorter than the long reign of hydrogen fusion. And once the helium is exhausted, the star faces another crossroads. Lower mass stars like the Sun do not have the gravitational heft to ignite further fusion stages. Instead, they shed their outer layers into space, creating a planetary nebula, a delicate, glowing shell of gas that surrounds the dense, cooling core. This exposed core becomes a white dwarf, a stellar ember glowing with residual heat. White dwarfs no longer produce energy through fusion, but they can persist for billions of years as they slowly cool and fade. They represent the final chapter in the life of a medium-sized star, a quiet coda to the vibrant symphony of nuclear fusion that once powered them. For the most massive stars, the story is more dramatic. Their cores can reach temperatures and pressures high enough to fuse elements beyond carbon and oxygen, building up layers of heavier elements like silicon, sulfur, and eventually iron. But fusion of iron does not release energy, it requires energy. When an iron core grows too massive, it can no longer support itself against gravity. In a matter of seconds, the core collapses in a catastrophic implosion, triggering one of the most powerful events in the universe, a supernova explosion. The outer layers of the star are hurled into space in an immense explosion, enriching the surrounding interstellar medium with heavy elements forged in the dying moments of the star. This process seeds the galaxy with the raw materials for new stars, planets, and life itself. What remains of the core depends on the mass of the original star. If it is below a certain threshold, it becomes a neutron star, a dense object composed almost entirely of neutrons, held together by gravity and the strong nuclear forces at the heart of matter. If the collapsing core is massive enough, no known force can stop its inward plunge. The core becomes a black hole, a region of space-time where gravity is so strong that not even light can escape. Black holes are among the most enigmatic objects in the cosmos, their presence inferred from the way they warp the fabric of space and influence the motion of nearby stars and gas. The life cycles of stars thus connect the smallest scales of nuclear interactions with the largest scales of galactic evolution. They are engines of creation and destruction, forging the elements in their cores and dispersing them in cosmic winds and violent explosions. The light of stars illuminates the history of the universe, carrying the signatures of these cycles across billions of years and countless light-years of space. The study of stellar life cycles is not merely an academic pursuit. It is a way of understanding the profound connections between the life of a star and the matter that makes up planets, oceans, and living beings. Every atom of carbon in our bodies, every molecule of oxygen we breathe was forged in the heart of a star that lived and died long before our solar system was born. This cosmic recycling links us to the distant past and to the ongoing processes that continue to shape the universe. Stars, in their majestic arcs of birth and death, tell a story that stretches beyond the confines of any single lifetime. They are not static points of light, but dynamic laboratories where matter is transformed, energies are released, and the building blocks of worlds are forged. Every stage of a star's life, every subtle shift in temperature and pressure, reveals a new chapter in this cosmic narrative, a new layer of complexity that reflects the ceaseless interplay of fundamental forces. The processes that govern a star's life cycle are driven by the delicate balance between gravity and the pressure of radiation and heat. In the early stages, gravity is the sculptor, shaping the chaotic gas clouds into dense cores and igniting the nuclear fires that bring light to the darkness. Over time, however, the balance begins to tilt. The fuel that powers the star's brilliance is consumed, the weight of gravity pressing ever more insistently inward. The star responds by reshaping itself, each new phase a testament to the unyielding laws of physics and the inexhaustible creativity of the cosmos. These changes are not abrupt, but occur over timescales that dwarf human history. a red giant's slow inflation, the collapse of a supergiant's core, the quiet fading of a white dwarf, each unfolds over millennia or longer. Process is so gradual that they seem almost eternal. Yet in these slow dances of matter and energy, there is constant motion, a continual reshaping of the universe that echoes the slow cycles of life and death on Earth. As stars evolve, they become crucibles for the creation of the elements that seed the cosmos with diversity and complexity. In the cores of massive stars, fusion reactions produce not just the light that illuminates the night sky, but the very atoms that make up planets, oceans, and living cells. The oxygen we breathe and the calcium in our bones were once forged in the hearts of stars, carried into space by supernovae and woven into new worlds by the quiet accretion of dust and gas. In studying these life cycles, astrophysicists are not merely cataloging distant phenomena. They are tracing the origins of everything familiar to us, finding in the death throes of ancient stars the seeds of future worlds. The data gathered by telescopes and instruments, spectra that record the light of stars, images that reveal their shapes and motions, are pieces of a puzzle that, when assembled, reveal the history of matter itself. The journey from a cool, dark cloud of gas to a shining star, and finally to a quiet remnant, is a journey that every star must take. Yet each path is unique, shaped by the star's mass, its environment, and the subtle currents of interstellar space. Even in the final stages, as a white dwarf cools or a neutron star spins down to silence, there are variations and subtleties that keep the story endlessly rich. These differences are not mere curiosities. They are clues to the processes that govern the cosmos, hints at the hidden laws that tie together the smallest scales of the atomic world and the grandest reaches of the galaxies. In these final remnants, there is a quiet dignity that belies the violence of their pasts. A white dwarf glows softly with the embers of a star's final light. A neutron star, dense beyond comprehension, spins with the momentum of a collapsed core, sending out pulses of radiation like the heartbeat of a dying giant. A black hole, shrouded in the darkness of its own gravity, warps the space around it in silent testimony to the power of collapse. These are the endpoints of stellar life, but they are also beginnings. The elements scattered by supernovae enrich the clouds of gas that will become new stars. The gravity of a black hole can gather matter into luminous disks that blaze with energy, shaping the cores of galaxies. In the quiet intervals between these cataclysms, the universe grows new structures from the debris of the old, each cycle building upon the last in a ceaseless dance of creation. Astrophysicists peer into these processes with instruments that can see far beyond the limits of human sight. They study the subtle shifts of spectral lines that reveal the fusion within stars, the ripples of gravitational waves that hint at the collapse of massive cores. In the data they gather, they find the signatures of ancient processes still at work today, shaping the future of the cosmos in ways both familiar and strange. And in this patient, methodical work, there is an echo of something deeper. Each measurement is an act of curiosity, each calculation a step in a journey that has no end. The story of the stars is the story of a universe in motion, of forces and energies that build and rebuild the cosmos in cycles that stretch across time and space. It is a story that began long before humanity learned to gaze at the night sky in wonder, and it will continue long after our brief moment has passed. Yet even in this grand scale, there is a thread of connection that runs through it all. The atoms that burn in the hearts of stars are the same atoms that flow through our bodies. The light that travels from a distant supernova is the same light that warms our skin on a summer day. In every spectrum, every image, there is a reminder that we are not separate from this cosmic dance, but participants in it, shaped by the same forces and bound by the same laws. In the quiet glow of a white dwarf, in the fierce brilliance of a supernova, in the cold gravity of a black hole, There is a lesson that transcends the numbers and equations. It is a lesson in patience and in perspective, a gentle reminder that even the mightiest stars must yield to the passage of time. And in that yielding, they give rise to new beginnings, to new possibilities written in the language of light and gravity. For in the end, the life cycles of stars are more than just an astrophysical phenomenon. They are a mirror of the cycles of life that unfold around us and within us, a testament to the quiet power of change and the enduring strength of connection. In their story, we find both our origins and our destiny, woven together in the silent, ceaseless symphony of the cosmos. Chapter 5. The Life Cycles of Galaxies, Growth and Transformation. Galaxies, those vast islands of stars and gas scattered throughout the universe, are not static structures. They are dynamic, evolving entities shaped by the forces of gravity, the birth and death of stars, and the subtle interactions that unfold across billions of years. The life cycles of galaxies are a story of growth and transformation, a narrative of change written in the light of countless stars. At the heart of every galaxy lies a collection of matter that binds together through gravity. Stars, gas, dust, and dark matter all contribute to the gravitational well that defines the galaxy's shape and structure. Yet even within this gravitational binding, galaxies are in constant motion. Stars orbit the center, gas clouds drift and collide, and entire spiral arms can sweep slowly around the core, creating the graceful patterns we see in the night sky. Galaxies begin their lives as small, irregular clumps of gas and stars. Over time, they grow and change through the process of accretion, gathering material from their surroundings. This growth can occur slowly as gas from the intergalactic medium falls inward, feeding the birth of new stars. In other cases, galaxies merge with one another, colliding and combining their masses in spectacular cosmic events. These mergers can transform the structure of galaxies, creating new shapes and triggering waves of star formation that light up the universe. As galaxies evolve, the forces that shape them operate on scales that stretch the imagination. The interactions of dark matter, though invisible to our instruments, sculpt the gravitational scaffolding that defines a galaxy's extent. It is this unseen framework that guides the motions of stars and gas, creating the potential wells where matter can gather and new stars can ignite. The birth of stars within a galaxy is a continuous process. In the dense molecular clouds that drift through spiral arms or nestle in irregular regions, gravity slowly coaxes gas into new generations of stars. These young stars often form in clusters, their light brightening the galactic disk and driving the cycles of energy that keep the interstellar medium alive with motion. Yet even as new stars emerge, older ones drift along their orbital paths, gradually aging and changing the composition of the galaxy itself. The death of stars also leaves its mark. Supernova explosions enrich the surrounding gas with heavy elements, while the gentle winds of aging red giants return material to the galactic medium. This ongoing exchange of matter, driven by stellar processes, seeds the galaxy with the ingredients for future generations of stars and planets. In this quiet recycling of gas and dust, galaxies continually reshape themselves, weaving new tapestries of light and matter with each cycle. Over time, galaxies can transform dramatically. The mergers of galaxies, while violent on a cosmic scale, are essential to their growth and evolution. When two galaxies collide, their stars pass through one another like ghosts, rarely colliding directly. Yet their gravitational fields tug and warp the shapes of their disks, creating streams of stars and vast tidal tails that arc outward like cosmic sculptures. In the heart of such a merger, gas can be driven inward, feeding bursts of star formation that light up the galaxy in waves of brilliant activity. These interactions do more than rearrange the visible matter. They can awaken the central black holes that lie hidden in the cores of many galaxies. As gas and dust funnel inward during a merger, These supermassive black holes can flare to life, consuming matter and releasing enormous amounts of energy. These active galactic nuclei, or quasars, can outshine the entire galaxy around them for a brief moment in cosmic time, their radiation blazing across the universe and reshaping the gas that surrounds them. Not all galaxies follow the same path. Some grow steadily, building up their disks over billions of years without major mergers to disrupt them. Others form elliptical shapes, their ordered rotations lost in the random motions of countless stars, a legacy of past collisions and the gravitational mixing of their orbits. Each galaxy carries within it the history of these interactions, an imprint of the forces that have shaped its evolution. Astronomers study these processes using observations across the electromagnetic spectrum. Radio waves reveal the cool gas that forms the raw material for future stars. Infrared light shows the hidden glow of dusty star-forming regions. X-rays trace the violent interactions of hot gas, while optical telescopes capture the graceful arcs of spiral arms and the shimmering glow of old stellar populations. Together, these observations allow scientists to piece together the life stories of galaxies, from their first stirrings of star formation to the quiet grandeur of ancient structures that drift slowly through the cosmic web. The environments in which galaxies live also play a role in their evolution. Galaxies in dense clusters feel the gravitational pull of their neighbors, their gas stripped away by the harsh winds of the intracluster medium. Others drift in relative isolation, their growth shaped more by slow accretion than by violent mergers. These differences create the diversity of galactic forms we see in the universe today. From the elegant spirals that whirl in quiet solitude to the massive ellipticals that dominate the crowded hearts of clusters. Galaxies are not static in their transformations. They breathe in the flow of gas that surrounds them, converting it into new generations of stars, and exhale it back in the form of supernova-driven winds and jets from active nuclei. These outflows can carry gas out of the galactic disk, shaping the surrounding intergalactic medium and feeding back into the broader cosmic ecosystem. In this interplay of inflows and outflows, galaxies are both sculptors and subjects, constantly remaking themselves and their surroundings in a quiet, patient dance. At the largest scales, galaxies themselves are not isolated islands, but are woven into the cosmic web, a vast network of filaments and voids that stretches across the observable universe. Galaxies gather along these filaments, where gravity pulls matter together in streams that feed their growth. In the quiet darkness between the filaments, voids expand, shaping the cosmic landscape like the empty spaces between brushstrokes on a canvas. As galaxies continue to evolve, their fates are intertwined with the surrounding environment. Some galaxies experience a gradual loss of gas, a gentle fading as their reservoirs of star-forming material become depleted. In this quiet senescence, galaxies grow old gracefully, their bright regions of star formation slowly giving way to the cooler glow of older stars. Others, however, find themselves in more tumultuous surroundings, where interactions and mergers can spark intense periods of activity. These periods of heightened star formation, known as starbursts, can briefly transform a galaxy's appearance. The inflow of gas fuels a frenzy of star birth, brightening the galaxy and creating powerful winds that blow material out into the intergalactic medium. These winds can quench the very process they ignite, carrying away the fuel for future stars and reshaping the galaxy's future evolution. In this balance of growth and regulation, galaxies find a kind of equilibrium, a cycle of creation and dispersal that echoes the processes seen in individual stars. The study of these transformations is a window into the nature of cosmic time. Unlike the brief human lifespan, the changes that sculpt galaxies unfold over billions of years. To glimpse this slow dance requires patience and the ability to see beyond the present moment. Astronomers turn their instruments to the most distant reaches of space, capturing the light of galaxies as they appeared in earlier epochs. In these ancient signals, they find the threads that connect the universe's past to its present. Each observation is a step along this journey of understanding. The careful measurement of light, the precise mapping of structure, these are the tools by which scientists unravel the history of galaxies. And in that history, they find clues to the broader questions that animate all of astrophysics: how matter organizes itself, how structure emerges from chaos, and how the seeds of complexity are sown in the vast fields of interstellar and intergalactic space. The light of galaxies carries within it the memory of these processes. In the shifting colors of a spectrum, in the subtle shapes of a spiral arm or the smooth glow of an elliptical, there are stories of birth and death, of collisions and calm intervals. Each galaxy is both an individual and a part of a larger whole, its life shaped by the collective behavior of matter and energy on scales that defy ordinary experience. This interplay of forces is not just a scientific curiosity. It speaks to a deeper harmony that underlies the universe, a quiet order that emerges from the complexity of countless interactions. In the shapes of galaxies and the patterns of their light, there is an echo of the same principles that guide the evolution of stars and the formation of planets. It is a reminder that in the grand tapestry of existence, every structure, no matter how vast, is connected to the smallest processes that shape the cosmos. For those who seek to understand these cycles, there is a reward that transcends the data and the models. It is the gentle wonder that comes from seeing the universe as a living, changing whole, a system in which growth and transformation are woven into the very fabric of space and time. It is a sense of belonging to something larger, a quiet affirmation that the same forces that sculpt galaxies also touch our own lives in subtle, profound ways. As the study of galaxies advances, new tools and observatories promise to extend our reach even further. Telescopes that peer deeper into space and instruments that capture the faintest whispers of light will reveal details of galactic evolution that were once beyond our grasp. Each new image, each new spectrum, will add another brushstroke to the portrait of the cosmos, filling in the details of a story that continues to unfold. In the quiet light of a distant galaxy, in the faint arcs of stars that trace its edges, there is a reminder that the universe is always in motion. It grows, it changes, and it carries forward the echoes of every cycle that has come before. And in those echoes, in the silent glow of starlight across the darkness of space, there is a promise that even as we measure and map, we are also a part of this ongoing dance. For in the end, the life cycles of galaxies are more than an academic puzzle. They are a testament to the power of connection, to the ways in which gravity and light weave the universe into a single, coherent whole. In the swirling arms of a spiral galaxy, in the gentle fade of an aging elliptical, we find not just distant objects of study, but reflections of the enduring processes that shape us all. And in those reflections, we are reminded that even in the vastness of space, the story of the cosmos is also the story of us. Chapter 6. The Power of Gravity, from Orbits to Collisions. Gravity is the force that sculpts the universe, shaping the paths of planets, the structures of galaxies, and the vast tapestry of cosmic evolution. It is the quiet, invisible hand that binds everything together, from the orbits of the smallest moons to the majestic arcs of galaxy clusters stretching across the cosmos. In astrophysics, understanding gravity is essential to explaining the motion of celestial bodies and the grand architecture of the universe itself. Gravity emerges from mass, drawing objects together across empty space. It pulls at the stars within galaxies, holding them in sweeping orbits that span thousands of light years. It binds planets to their stars, creating the cycles of seasons and the rhythms of day and night, that mark the passage of time. It is the engine that drives the collapse of gas clouds to form new stars, the sculptor of planetary systems, heat, and the keeper of cosmic order. From the smallest scales to the largest, gravity dictates how matter organizes itself. In the solar system, gravity is the choreographer of planetary motions. It guides the Earth in its yearly journey around the sun, holds the moon in its monthly dance across the sky, and governs the paths of comets and asteroids that wander through the darkness. These motions are not static. They shift and change, each orbit a delicate balance between inertia and the pull of gravity's invisible embrace. Beyond the familiar neighborhood of the solar system, gravity exerts its power on grander scales. In the hearts of galaxies, it gathers matter into swirling disks of stars and gas, giving rise to the elegant spirals that arc across the night sky. In massive galaxy clusters, gravity pulls hundreds or thousands of galaxies into vast congregations, shaping the cosmic landscape with the slow, steady hand of attraction. These colossal structures are born of gravity's patient work, built up over billions of years of gentle pulls and quiet growth. Gravity also has the power to warp the very fabric of space and time. Einstein's general theory of relativity revealed that gravity is not merely a force acting at a distance, but a manifestation of space-time curvature. Massive objects bend the geometry around them, altering the paths of light and the motions of bodies in their vicinity. This bending of light by gravity, known as gravitational lensing, allows astronomers to peer deeper into the universe by magnifying distant galaxies and revealing the shapes of structures otherwise hidden from view. The subtle warping of space-time can be seen in the orbits of stars near massive objects. In the centers of galaxies, stars dance around supermassive black holes, their paths curving under the influence of gravity's deepest wells. Observing these orbits reveals the presence of black holes too dark to see directly, their gravity betraying their existence as it shapes the dance of the stars around them. Gravity's influence extends beyond shaping orbits and clusters. It is also the driver of collisions, the silent force that pulls galaxies together and sends stars plunging toward one another. When galaxies merge, gravity choreographs a complex dance of interactions, drawing streams of stars into graceful arcs and hurling others into new orbits. These cosmic collisions are slow, stately affairs, unfolding over hundreds of millions of years. Yet their effects are profound, reshaping galaxies and triggering bursts of star formation that light up the universe. In smaller scales, gravity sculpts the structures of planetary systems. The early solar system was a swirling disk of gas and dust, where gravity gathered material into clumps that grew into planets and moons. The same process unfolds around distant stars as protoplanetary disks become the nurseries of new worlds. In these quiet cradles of gravity, matter coalesces and organizes, guided by the same invisible force that holds entire galaxies together. The beauty of gravity's power lies in its universality. It acts on all matter, regardless of its form or location, weaving together the cosmic fabric into patterns of motion and structure. In the delicate balance of forces that shape an orbit, in the grand collisions that birth new galaxies, there is a quiet order that emerges from gravity's patient pull. Astronomers measure gravity's effects with instruments of precision and sensitivity. They chart the motions of planets and moons, trace the paths of stars in distant galaxies, and watch for the subtle bending of light that reveals the presence of massive structures. These observations are windows into the workings of gravity, revealing its role as the silent architect of the cosmos. In the slow arcs of planets around the sun, in the majestic spirals of galaxies, in the deep wells of gravity that swallow even light, there is a continuity of form and motion that echoes across the universe. It is a language of curves and orbits, of gentle pulls and violent collisions, written in the quiet movements of matter and the patient shaping of time itself. Gravity is also the silent witness to the most energetic events in the universe. When massive stars exhaust their nuclear fuel and collapse, it is gravity that drives the formation of neutron stars and black holes. In these final acts of stellar evolution, gravity reveals its dual nature. It is both the creator of stability and the agent of transformation. The collapse of matter under gravity's relentless pull is a moment of violence and birth, creating some of the most extreme objects known. These objects, born of gravity's ultimate embrace, become laboratories for the testing of our deepest theories. Black holes, in particular, challenge our understanding of space and time. Their gravity is so strong that it creates a region from which nothing can escape, not even light. Yet it is also in these places that we see the unity of physics, where the elegant equations of relativity meet the strange probabilities of quantum mechanics. In these cosmic mysteries, gravity remains a guiding force, leading scientists to new frontiers of discovery. Gravity's reach is not limited to dramatic events. It also shapes the more familiar motions of everyday life. On Earth, it gives weight to our steps and defines the shapes of rivers and mountains. It binds the oceans to the planet, sculpting the tides that move in gentle rhythms. In the constant pull we feel as we stand on the ground, we are connected to the same gravity that shapes galaxies and bends the paths of light. In the modern era, our understanding of gravity has deepened with precision measurements and careful observations. Space missions have mapped the subtle variations in Earth's gravitational field, revealing the hidden patterns of mass that shape our planet. These measurements, combined with observations of distant stars and galaxies, create a tapestry of gravitational forces that stretch from our world to the furthest reaches of the cosmos. The study of gravity is a study of motion and stability, of cycles and transformations. It is a quiet exploration of the forces that shape existence, revealing that the universe is not a static backdrop but a dynamic dance of matter and energy. In every orbit traced by a planet, in every slow drift of a galaxy across the sky, there is a story of gravity's patient work. This patient work is not uniform. In regions where mass gathers, gravity creates order out of chaos, drawing matter together and forging new structures. In the emptier spaces between, gravity's gentle pull shapes the slow expansion of voids, creating the balance that defines the large-scale structure of the universe. These patterns of motion and rest, of attraction and distance, echo across the cosmos in forms both subtle and grand. Gravity is also the quiet link between past and future. The motions it dictates today are the echoes of ancient forces, the inherited paths of matter that has danced to its rhythm since the dawn of time. In the slow spirals of galaxies and the patient curves of planetary orbits, there is a memory of the forces that shaped them long ago. And in that memory, there is the promise of change yet to come. As we observe the universe and map the patterns of motion, we are also mapping the reach of gravity. Each star's orbit, each planet's path, each flicker of light bent by a distant cluster is a testament to gravity's presence and power. These observations are not just data. They are glimpses into the deep workings of the cosmos, a window onto the invisible currents that shape everything we see. In the end, gravity is more than just a force. It is a quiet companion to existence itself, an ever-present reminder of the connections that bind all things. In its silent embrace, we find both the familiar comfort of Earth and the strange majesty of distant galaxies. And in that duality, there is a gentle whisper that speaks to the deepest parts of our curiosity, a reminder that in every fall of an apple and every drift of a star, we are touching the same force that shapes the destiny of the universe. For in gravity's patient pull, there is a story that reaches across the scales of existence. It is a story written in the arcs of orbits and the gentle curves of space, in the slow collapse of a star and the vast collisions of galaxies. It is a story that, even as we measure and model it, invites us to wonder at the quiet elegance that shapes the cosmos. And in that wonder, we find a connection that ties our own small world to the infinite expanse of the universe. Chapter 7. Dark Matter and Dark Energy, the Unseen Components. The universe we see is only a small fraction of what truly exists. When we look up at the night sky, we see stars and galaxies, nebulae glowing softly against the dark canvas of space. But these luminous objects, no matter how countless they appear, are merely the visible face of a cosmos that holds far more than what meets the eye. Hidden within the fabric of space are vast, unseen components, dark matter and dark energy, that shape the destiny of the universe and challenge our understanding of reality itself. Dark matter reveals itself not through light, but through its gravitational pull. It neither emits nor absorbs light in any form, making it invisible to even the most sensitive telescopes. Yet its presence can be inferred from the way galaxies rotate, from the motions of stars at their edges, and from the bending of light that passes through regions of intense gravity. These observations show that the luminous matter we can see, stars, gas, and dust, accounts for only a small portion of the gravitational mass required to hold galaxies together. The evidence for dark matter first emerged in the early studies of galaxy rotation curves. Astronomers expected that the speed of stars orbiting in a galaxy would decrease with distance from the center, just as the outer planets in the solar system move more slowly around the sun. Instead, they found that stars far from the center moved as quickly as those closer in. This unexpected observation implied that an unseen mass was providing the necessary gravitational pull, an invisible halo of dark matter that envelops each galaxy. Further clues to dark matter's presence come from gravitational lensing. Light from distant galaxies is bent as it travels through regions of strong gravity, creating distortions and arcs in the images we observe. The magnitude of this bending reveals the total mass present along light's path, and again, visible matter alone cannot account for the effect. The missing mass, inferred from the bending of light itself, is attributed to dark matter. Dark matter also plays a crucial role in the formation and evolution of cosmic structures. In the early universe, slight variations in density provided the seeds for the growth of galaxies and clusters. These variations, magnified over time by the gravitational pull of dark matter, guided the formation of the cosmic web, the vast network of filaments and voids that stretches across the observable universe. Without dark matter's stabilizing gravity, these structures could never have formed as we see them today. Despite its profound influence, the nature of dark matter remains a mystery. It does not interact with light, and it appears to pass through ordinary matter with hardly a trace. Physicists have proposed a variety of candidates for dark matter's identity, from exotic particles beyond the standard model of physics to primordial black holes that formed in the earliest moments after the Big Bang. Experiments on Earth and observations in space continue to search for clues, hoping to reveal the true nature of this hidden substance. As scientists delve deeper, they deploy sensitive detectors in deep underground laboratories, shielded from the noise of cosmic rays. These instruments wait for the faintest interactions between dark matter particles and atomic nuclei, tiny collisions that would reveal their presence. At the same time, particle accelerators strive to create conditions that might produce these elusive particles, offering another path to uncovering their identity. Dark matter's partner in the cosmic balance is dark energy, a force that works in an entirely different way. While dark matter binds galaxies together, dark energy drives the expansion of the universe itself. Its discovery came not from the study of galaxies, but from the observations of distant supernovae, stellar explosions that act as cosmic mileposts. These observations showed that the universe's expansion, is accelerating, pushed apart by a repulsive energy that pervades space itself. Dark energy is even more enigmatic than dark matter. It does not clump or gather like matter does, and it cannot be traced through gravitational lensing. Instead, it is a smooth, uniform presence woven into the very fabric of space. The simplest explanation is that it represents a fundamental property of space itself, a cosmological constant that Einstein once proposed, then set aside, and which modern observations have now resurrected as a central component of our cosmic story. The impact of dark energy is profound. It shapes the ultimate fate of the universe, dictating whether expansion will slow and reverse or continue to accelerate forever. Current evidence suggests that dark energy will continue to drive the universe outward, stretching space itself and carrying galaxies further apart in a slow, inexorable drift. In this future of endless expansion, galaxies will fade beyond sight, and the universe will grow ever colder and darker. The presence of dark energy also offers clues to the very structure of space and time. It suggests that space itself is not empty, but infused with a quiet, persistent energy that shapes the motion of galaxies and the unfolding of cosmic history. The equations that describe dark energy are simple, yet they hint at a deeper truth, one that connects the smallest quantum fluctuations with the grand arcs of the universe's expansion. Together, dark matter and dark energy compose the vast majority of the universe's contents. Ordinary matter, the atoms that make up stars, planets, and life itself, accounts for only a small fraction. This realization is a humbling shift in perspective. Most of what exists is hidden from direct observation, accessible only through the subtle clues of motion and structure that reveal the presence of the unseen. Astronomers and physicists continue to search for direct evidence of dark matter. Deep underground detectors, shielded from cosmic rays and noise, wait for the faintest interactions between dark matter particles and ordinary matter. Space telescopes scan the cosmos for telltale signals that might hint at dark matter's identity. These experiments are exercises in patience and precision, requiring years of observation to test theories that reach to the edges of known physics. Meanwhile, the study of dark energy pushes the boundaries of cosmology and our understanding of fundamental forces. Its very nature challenges the foundations of physics, suggesting that our grasp of gravity and the structure of space may be incomplete. The equations that describe dark energy's behavior are elegant in their simplicity, yet they remain placeholders for a deeper truth still waiting to be revealed. The interplay of dark matter and dark energy is not a mere curiosity. It is a window into the ultimate questions of existence. Their invisible forces shape the past and the future, determining the growth of galaxies, the fate of stars, and the long arc of cosmic evolution. They are reminders that the universe is more mysterious than we can easily grasp, and that our understanding is always a work in progress. In the quiet night sky, as we peer into the darkness between the stars, we sense the vastness of these mysteries. We see the gentle glow of starlight, the faint arcs of distant galaxies, and we know that beyond this light, there is an invisible dance that shapes everything. In these moments of reflection, there is both humility and awe, a recognition that the universe is filled with forces we cannot yet see, but that nonetheless guide the rhythm of creation. For in the end, the study of dark matter and dark energy is more than a scientific quest. It is a meditation on the nature of existence itself. In these unseen components, we find a reminder that the universe is not only vaster than we imagine, but deeper and more interconnected than we can fully comprehend. It is a gentle echo of the truth that even in the darkness, there is structure and purpose, an unseen dance that guides the stars and whispers of the mysteries yet to be revealed. Chapter 8. The Expanding Universe, Hubble's Law and Cosmic History. The discovery that the universe is expanding was one of the most profound shifts in our understanding of the cosmos. It transformed our view of the universe from a static stage to a dynamic, evolving entity. At the heart of this discovery lies Hubble's law, a relationship that connects the distances of galaxies to the speeds at which they are receding from us. This simple observation has opened a window onto the history of the cosmos and provided a framework for understanding its past, present, and future. Hubble's law is based on the observation that galaxies are moving away from us, and that the farther away they are, the faster they recede. This relationship was first identified by Edwin Hubble in the 1920s, using observations of distant galaxies and the redshifts in their light. These redshifts, which indicate that the light's wavelength has been stretched, reveal that space itself is expanding, carrying galaxies with it like dots on the surface of an inflating balloon. This expansion is not a motion through space, but an expansion of space itself. Galaxies are not traveling through a static backdrop. Rather, the very fabric of space is stretching, creating more distance between galaxies over time. This concept is subtle and profound, requiring a shift in perspective to truly grasp its implications. It means that the universe has no center or edge in the traditional sense, and that every observer sees the same general pattern of expansion, regardless of their location. The measurement of this expansion has been refined over the decades. Observations of distant supernova, the cosmic microwave background radiation, and large-scale structures have all contributed to a more precise determination of the rate of expansion, known as the Hubble constant. This constant is a crucial parameter in cosmology, shaping our understanding of the universe's age, its contents, and its ultimate fate. The expansion of the universe carries with it the echoes of its beginning. The light we see from distant galaxies has traveled for billions of years, bringing with it a snapshot of the universe as it was long ago. In this ancient light, we see the story of cosmic evolution unfold. The birth of galaxies, the formation of stars, and the slow gathering of matter into the structures we observe today. The cosmic microwave background, a faint glow that fills the universe, is a remnant of the earliest moments after the Big Bang. It is the afterglow of a time when the universe was hot and dense, a time when light and matter were intertwined in a bright, uniform sea. As the universe expanded and cooled, this light was released, stretching into the microwave wavelengths we observe today. It carries with it a record of the conditions that existed when the universe was only a few 100,000 years old. In the decades since Hubble's discovery, astronomers have used the expanding universe as a tool to probe its history and structure. The distribution of galaxies, the clustering of matter, and the faint ripples in the cosmic microwave background all provide clues to the processes that have shaped the universe over billions of years. Each observation adds a piece to the puzzle, revealing the interplay of gravity, radiation, and dark energy that governs the cosmic tapestry. The expansion of the universe also has profound implications for its ultimate fate. If the expansion continues unchecked, galaxies will drift ever farther apart, their light redshifted into oblivion as the universe grows colder and darker. If gravity can halt or reverse the expansion, the universe might eventually collapse back upon itself, ending in a final moment of heat and density. Current observations suggest that the universe's expansion is accelerating, driven by the mysterious force of dark energy that permeates space. Astronomers have refined their observations of cosmic expansion through multiple lines of evidence. Supernova, used as cosmic distance markers, reveal the acceleration of this expansion. The large-scale distribution of galaxies, mapped in intricate detail by surveys that span vast swaths of sky, shows the subtle flows of matter shaped by gravity's patient pull and the relentless push of expansion. Each measurement adds clarity, filling in the outlines of a universe that has been growing since its fiery birth. One of the most profound insights of this expanding cosmos is that looking deeper into space is also looking further back in time. The finite speed of light means that distant galaxies show us their younger selves, snapshots of their early days frozen in the light that finally reaches us. In this way, the night sky becomes a window into cosmic history, a record of change written across billions of years. This realization brings with it a sense of continuity. The galaxies we see as faint smudges of light in the darkness are ancient, their stories unfolding long before Earth formed from the dust of earlier generations of stars. Their light carries the memory of beginnings, of turbulent collisions and slow, graceful growth. In the deep silence of space, the expansion of the universe becomes a quiet testament to the persistence of motion and the enduring nature of change. Yet the expanding universe also brings into focus the great mysteries that remain. The precise rate of expansion, captured in the Hubble constant, is still a topic of careful study and spirited debate. Different methods of measuring it, from the flickers of supernova to the echoes of the cosmic microwave background, give subtly different answers. These discrepancies hint at possible new physics, at layers of understanding yet to be uncovered. The expansion of the universe is not just a matter of galaxies drifting apart. It is a fundamental feature of space-time itself. In the mathematical language of general relativity, the metric of the universe is dynamic, evolving with time as it responds to the interplay of matter, radiation, and dark energy. This expansion carries galaxies along with it like dust motes in a rising tide, their motions a reflection of the geometry of space. Cosmic expansion also shapes the large-scale structure of the universe, the grand tapestry of voids and filaments that stretches across the night sky. Gravity, working slowly over eons, gathers matter into clusters and threads, while expansion ensures that the spaces between grow ever wider. This balance of attraction and growth creates the cosmic web we observe, a structure that is both ancient and still evolving. For astronomers, measuring the expansion of the universe is a way to test the fundamental theories that describe reality. It connects observations of distant galaxies with the early moments of the cosmos, when quantum fluctuations became the seeds of all future structure. In the stretching of space, we find a record of those earliest times, a faint but persistent memory of the birth of the universe. As technology advances, new instruments promise even greater insights into the expanding universe. Space-based telescopes peer deeper into the darkness, capturing the faint glimmers of galaxies that formed when the universe was young. Observatories on Earth use the subtle wiggles in the distribution of galaxies, traces of sound waves frozen into cosmic structure, to measure the expansion with ever greater precision. Each new observation refines our picture, revealing not just the motions of galaxies, but the quiet workings of the forces that shape everything we see. It is a journey of curiosity, of patient exploration, driven by the human spirit's desire to understand the patterns that stretch across the cosmos. In the quiet depths of space, the expansion of the universe whispers of our place in a cosmos that is at once vast and connected. We are part of this growth, born from the same processes that shaped the first stars and galaxies. In the faint glow of distant light, there is a reminder that the universe itself is a story in motion, one that began in a blaze of creation and continues to unfold in every corner of the sky. For in the end, the expanding universe is not just a scientific observation. It is a reflection of the quiet power of motion and change, of the deep forces that weave together time and space. It is a story of growth and transformation, written in the language of redshift and distance, of light that journeys across the darkness to whisper of beginnings and of possibilities yet to come. Chapter 9. Black holes and neutron stars, extreme physics in action. Black holes and neutron stars are the most extreme manifestations of gravity's relentless pull, regions of the cosmos where the usual rules of matter and energy reach their limits. They are the final products of stellar evolution for the most massive stars, born from the deaths of these giants in supernova explosions. In these dense remnants, matter is compressed to extraordinary densities, and the familiar world of atoms and molecules gives way to the deep and mysterious domain of fundamental physics. A neutron star is the collapsed core of a massive star that has exhausted its nuclear fuel. When fusion can no longer resist gravity, the core implodes, crushing protons and electrons together to form neutrons. The result is a sphere of matter so dense that a single teaspoon would outweigh a mountain. Despite this density, neutron stars are only a few kilometers across, making them incredibly compact. They spin rapidly, sometimes hundreds of times per second, and possess magnetic fields trillions of times stronger than any magnetic field found on Earth. Black holes, by contrast, represent an even more dramatic endpoint. When the core of a collapsing star exceeds a certain mass, no known force can withstand the inward pull of gravity. The collapse becomes unstoppable, compressing matter into a singularity, a point of infinite density and zero volume. Surrounding this singularity is the event horizon, a boundary beyond which nothing, not even light, can escape. Black holes are invisible to direct observation, yet their presence is revealed by the way they warp the motions of nearby matter and the light that passes close to them. These exotic objects are not merely curiosities. They are natural laboratories for testing the boundaries of physics. In the intense gravity near a neutron star, matter behaves in ways that challenge our understanding of nuclear forces and quantum mechanics. The crust of a neutron star is a lattice of atomic nuclei crushed together, while its core may harbor states of matter that exist nowhere else in the universe. Observing neutron stars provides insights into the behavior of matter at the highest densities known. Black holes, too, are windows into fundamental physics. The warping of space-time near their event horizons causes time to slow and space to stretch. Light emitted near a black hole is redshifted, losing energy as it climbs away from the intense gravity. Matter that falls toward a black hole forms a swirling disk, heating up as it spirals inward and radiating energy across the spectrum. These accretion disks can outshine entire galaxies, revealing the black hole's hidden presence. Despite their reputation as cosmic devourers, black holes can also shape their environments in more constructive ways. Jets of particles can erupt from the regions near the event horizon, streaming across interstellar space at nearly the speed of light. These jets are driven by the intense magnetic fields and the rotation of the black hole itself, and they can carry energy far from the black hole's immediate surroundings. In galaxies with active black holes at their cores, these jets help regulate star formation and shape the structure of the surrounding gas. Observing these extreme environments requires innovative techniques and cutting-edge technology. Telescopes sensitive to X-rays and gamma rays can capture the high-energy emissions from matter near a black hole or the powerful magnetic storms on a neutron star's surface. Radio telescopes can detect the pulses of neutron stars known as pulsars, rhythmic beacons that reveal the precise rotations of these dense remnants. The detection of gravitational waves has added a new dimension to the study of black holes and neutron stars. When two of these dense objects spiral together and merge, they create ripples in the fabric of space-time itself. These waves, first detected in 2015, offer a new way to observe the universe, a way that does not rely on light, but on the very structure of space-time. Each detection is a glimpse into the cataclysmic collisions that shape the cosmos, revealing the masses and spins of the objects involved. The intense gravity near a neutron star bends the paths of light, creating a distorted view of the star's surface, known as gravitational lensing. In this strange geometry, we can see more than half of the neutron star at once, as light from the far side is bent back toward us. This effect allows astronomers to probe the shapes and temperatures of neutron stars, adding another layer of data to our understanding of their structure. Neutron stars also possess magnetic fields of staggering strength, billions of times stronger than any magnet on Earth. These fields channel streams of particles into intense beams of radiation, creating the pulsars that sweep the sky with their steady pulses. The regularity of these pulses is so precise that they rival the accuracy of atomic clocks, providing natural beacons for navigation and timing across the galaxy. Black holes, while invisible to direct observation, reveal themselves through their effects on nearby matter. The accretion disks that form around them can blaze with X-rays and gamma rays as matter is torn apart and heated to extraordinary temperatures. These emissions, flickering and shifting in intensity, provide indirect glimpses of the processes unfolding near the event horizon. In some galaxies, supermassive black holes millions of times the sun's mass anchor the cores, their gravity guiding the motions of stars and gas on scales that span thousands of light years. The study of these objects is not limited to astronomy alone. Physicists see in black holes and neutron stars the convergence of gravity and quantum mechanics, two pillars of modern physics that have yet to be fully reconciled. The event horizon of a black hole, for example, poses deep questions about the nature of information and its fate in the universe. Theorists propose that black holes may encode information about everything they consume, a puzzle that touches the foundations of how the universe stores and transforms information. The ongoing search for answers has driven astronomers and physicists to build ever more powerful observatories, peering deeper into the cosmos and capturing the faintest signals. Space-based telescopes that orbit above the Earth's atmosphere collect X-rays and gamma rays undimmed by the air, while radio observatories on the ground stretch their antennas across vast distances to catch the whispers of pulsars and the echoes of colliding neutron stars. In these observations, every photon and every wave carries the signature of processes so intense that they strain the very fabric of space and time. Each new piece of data refines our understanding, allowing us to test theories of gravity in the most extreme conditions known to nature. And in these tests, there is a profound sense of humility. For even in these violent, energetic regions, the same laws of physics that govern a falling apple or a planet's orbit apply. The universe does not reveal its secrets easily. The light from matter swirling into a black hole is fleeting, its patterns shifting in response to chaotic flows of gas and magnetic fields. The pulses of a neutron star may wink out in an instant, hidden by the star's own changes or swallowed by a companion's embrace. Yet with patience and precision, astronomers gather these faint signals, building a picture of a cosmos that is always moving, always changing. Black holes and neutron stars also show us how the universe recycles and transforms. The energy unleashed in a supernova not only creates these dense remnants, but seeds the surrounding space with the heavy elements that will become planets, oceans, and life itself. In the jets from black holes, in the winds that blow from neutron stars, there is a cosmic breath that stirs the galaxy, shaping clouds of gas and kindling the birth of new stars. In the quiet intervals between these cataclysms, there is a kind of cosmic patience. A neutron star spins down over millions of years, its magnetic field slowly unwinding. A black hole waits, invisible and silent, until a stray cloud of gas drifts too close and becomes a bright flare in the darkness. These rhythms of activity and quiet are written into the history of galaxies, a record of the ways matter and energy find balance across time. At the heart of this study is a profound question. What does it mean for matter to be so dense that it becomes a singularity, or so ordered that its pulses become cosmic metronomes? Black holes and neutron stars challenge our ideas of what is possible, showing us that even the most familiar substances can transform into states so alien that they defy direct comprehension. In their gravity, we glimpse the unity of physics, a dance of forces that binds the smallest scales of quantum mechanics to the largest curvatures of space-time. This is not only a scientific journey, but also a quiet meditation on extremes. We marvel at the neutron star's steady glow and the black hole's silent pull, and we recognize that in these distant objects are echoes of the same forces that shape our world. The same gravity that binds us to the Earth binds stars to the galaxy and draws matter into the final darkness of a black hole. In the end, the study of black holes and neutron stars is a testament to curiosity and the willingness to look beyond the visible. It is a journey into the heart of the universe's most extreme environments, a search for the quiet laws that govern even the loudest explosions. And in that search, we find a gentle truth: that even in the fiercest forces of nature, there is an order and a balance that speaks to something deeper than chaos. For in the silent hearts of black holes and in the flickering pulses of neutron stars, there is a story that stretches across the scales of existence. It is a story of collapse and rebirth, of the quiet dignity of matter reshaped by gravity and time. And in that story, we are reminded that even in the darkest reaches of space, there is structure, there is motion, and there is the quiet promise of understanding yet to come. Chapter 10. The Cosmic Microwave Background. The cosmic microwave background, CMB, is a faint, ancient light that permeates the entire universe, offering an unparalleled glimpse into the cosmos' earliest moments. It is the remnant glow of the primordial fireball that once filled all of space, released when the universe was just a few 100,000 years old. As the oldest light we can observe, the CMB holds the keys to understanding the birth, composition, and ultimate fate of the universe. By studying its patterns and temperature fluctuations, astronomers can reconstruct the cosmic story from its infancy to the complex structure we see today. The cosmic microwave background, often called the afterglow of the Big Bang, is one of the most profound discoveries in modern astrophysics. It is a faint, pervasive radiation that fills the entire sky, a whisper from the earliest moments of the universe's history. This ancient light offers a direct glimpse into a time long before stars or galaxies had formed, a time when the universe was still a hot, dense sea of particles and radiation. Discovered by accident in 1965 by Arno Penzias and Robert Wilson, the cosmic microwave background provided the first concrete evidence that the universe had a beginning, a moment when everything was compressed into a single, dense point and began to expand outward. This radiation is remarkably uniform, yet subtle variations in its temperature reveal the seeds of structure that would eventually grow into galaxies, stars, and planets. The cosmic microwave background is not light in the sense that we see with our eyes. Instead, it is microwave radiation, stretched by billions of years of cosmic expansion from the brilliant glow of a plasma-filled universe to the gentle hum that now pervades space. This transformation of the light's wavelength is a record of the universe's growth, a signature of the slow cooling that has unfolded over billions of years. As the universe expanded and cooled, it reached a point when matter and radiation could decouple, when protons and electrons combined to form neutral atoms, allowing light to travel freely for the first time. This moment, known as recombination, occurred when the universe was only a few 100,000 years old. The light released in that era has been traveling through space ever since, stretched and redshifted by the expansion of the cosmos. Today, the cosmic microwave background is remarkably uniform, with a temperature just a few degrees above absolute zero. Yet, it is not perfectly smooth. Tiny fluctuations in its temperature detected by sensitive instruments represent the first faint ripples of structure, These subtle variations reveal how matter was distributed in the early universe and how gravity would later amplify those seeds into the vast cosmic structures we see today. Observing the cosmic microwave background requires instruments capable of measuring minute differences in temperature across the sky. Satellites like COBE, WMAP, and Planck have mapped these fluctuations with exquisite precision, creating detailed images of the universe as it appeared long before the first stars were born. These maps are not just beautiful pictures, they are scientific treasure troves that encode the fundamental properties of the cosmos. From the tiny fluctuations in the cosmic microwave background, scientists can deduce the composition of the universe, the relative amounts of dark matter, dark energy, and ordinary matter. They can measure the universe's geometry, revealing whether space is curved or flat on the largest scales. They can also trace the history of cosmic expansion, using the patterns imprinted in this ancient light as a guide to the universe's growth over billions of years. The cosmic microwave background is a window into the universe's infancy, but it also connects us to its later evolution. The light we see today has been traveling across the cosmos for nearly 14 billion years, carrying with it a memory of the universe's first moments. In every direction we look, this faint glow surrounds us, a soft echo of a time when the cosmos was young and unformed. Yet this quiet light is not static. It bears the imprints of everything that has happened since it was released. As it traveled through space, the cosmic microwave background passed through clusters of galaxies and clouds of gas, picking up subtle distortions along the way. These distortions, known as the Sunyaev-Zeldovich effect and gravitational lensing, allow astronomers to use the cosmic microwave background as a probe of the large-scale structures that have grown over cosmic time. In the delicate patterns of the cosmic microwave background, scientists see the faint signature of primordial sound waves, pressure ripples that echoed through the hot plasma of the early universe. These acoustic oscillations, frozen into the temperature variations we measure today, reveal the density and composition of matter in the young cosmos. They are a testament to the dynamism of the early universe, a record of the push and pull that shaped everything that followed. As our instruments have become more sensitive, the cosmic microwave background has revealed even more subtle features. Tiny variations in its polarization, how the light waves are oriented, offer new clues to the physics of the early universe. These measurements can test theories of cosmic inflation, a period of rapid expansion thought to have occurred in the first moments after the Big Bang. If inflation occurred, it would have left a faint but distinct imprint in the polarization of this ancient light. The study of the cosmic microwave background is not merely a technical achievement. It is a journey into the deepest reaches of cosmic history. The data it provides have become a cornerstone of modern cosmology, forming the foundation for our understanding of how the universe has grown and changed. Each measurement, each map of subtle variations is a window onto the forces that have shaped existence on the largest scales. The search for answers in the cosmic microwave background has also pushed the boundaries of technology. Instruments must be cooled to near absolute zero to detect the faintest signals, shielded from the noise of Earth's atmosphere and our own electronics. The precision required to measure tiny differences in temperature across the sky challenges engineers and scientists alike, driving innovation and collaboration across fields. Through these efforts, we have learned that the universe is not a static backdrop, but a living, evolving system. The cosmic microwave background is a snapshot of its earliest form, yet it is also a reflection of the dynamic processes that have shaped everything since. It tells a story of growth and structure, of the quiet forces that turn simplicity into complexity. In the quiet glow of this ancient light, there is a reminder that the universe is both vast and intimately connected. The photons that fill the sky today have journeyed across time, carrying with them a memory of the birth of everything we know. They speak of a time when matter and energy were woven together, when the seeds of galaxies were planted in the soft murmur of plasma. For those who study this faint glow, there is both challenge and wonder. The data reveal the echoes of a cosmic dawn, yet they also whisper of mysteries still beyond reach. Each new observation refines the picture, but also reminds us of how much remains to be discovered. The cosmic microwave background is both a map and an invitation, a map of what has been and an invitation to keep looking deeper. In the end, the cosmic microwave background is more than a remnant of the past. It is a quiet testament to the endurance of light and the patient unfolding of the cosmos. It is a gentle echo of creation itself, a glow that ties us to the very birth of time and space. And in that soft, pervasive glow, there is a promise that even in the vast cold of the universe, there is still warmth, a warmth that began in the first fire of the cosmos and that will forever link us to the mystery of what lies beyond. Thank you for joining me on this peaceful journey through the cosmos, friend. As you drift off to sleep, may your dreams be filled with starlight and the quiet wonder of the universe. Sleep well, and may the mysteries of the night sky keep you company until we meet again.